In the previous video, we saw how to calculate the partitional equilibrium of the Crawford-Sobel model. Yes, and basically we found that we have to exploit the indifference property at the thresholds. That gives us this difference equation, and we solve the difference equation to find the equilibrium. So in this video, I'm going to talk about the welfare properties of the Crawford-Sobel equilibrium. Okay, now in any incomplete information model, there are multiple notions of welfare. There's ex-ante welfare, there's interim welfare sometimes, and then there's ex-post welfare. Ex-post welfare is after everything gets resolved, some random variable gets realized, like theta in this model. So the state of the world becomes known and the game plays out. At the very end, what is the welfare of each player, the sender and the receiver? That's called ex-post welfare. But you can also calculate welfare before theta gets realized. Okay, so we know how the game will play out, what its equilibrium is, but suppose theta has not yet been realized. In fact, of course, receiver doesn't know theta, that's the nature of the game, but suppose even the sender hasn't yet learned theta. But the sender knows what the equilibrium looks like, so the sender knows that once she learns the state of the world, the value of theta, she can only convey information in coarse intervals, like the equilibrium that we worked out. So looking ahead, that's what the sender sees. But the sender hasn't yet learned what the value of theta is. And at that point, the sender can calculate her expected payoff, taking into account all possible values of theta and the outcome that will arise in equilibrium. Right? So that is the sender's ex-ante welfare, and the same notion can be applied also to the receiver. The game hasn't been played out yet, but the receiver knows the structure of the equilibrium, so she calculates her payoff, her expected payoff, over all possible values of theta. So that's ex-ante welfare. So those are the two things that we are going to look at and calculate now. Just to avoid confusion, as the game is being played, at some point the sender will learn theta. Okay, but when we are calculating welfare in the next couple of slides, we will assume that theta has not yet become known to anyone, including the sender. Okay, how do we calculate the receiver's welfare? Which is ex-ante expected payoff, as I said. Now we know that once theta gets realized, it will fall in one of those intervals that arise in equilibrium. And depending on which interval it falls in, there will be some action chosen and some welfare will arise. So we're going to do it in two steps, right? We are going to take any particular interval which is part of the equilibrium. First, what is the expected welfare if theta is known to belong to one of the equilibrium intervals? Maybe the leftmost or the second from left, one of those. So we'll calculate conditional expected welfare for each of the intervals, right? For if theta belongs to this the first interval, this is the receiver's welfare expected. If it belongs to the second, if it belongs to the third, and so on and so forth. So we'll calculate conditional welfare for each interval, and then we'll put it together. Then we'll take expectations over all the intervals and calculate the overall expected payoff of the receiver. So suppose theta has been known to come from an interval of length x. Okay, that interval can be anywhere. What really matters is its length. Okay, so we'll pretend that the interval is from 0 to x. That's where theta has been drawn from. Now we have a uniform distribution. So if the interval that has arisen is 0 to x, then the action will be the midpoint of that interval, which is x by 2. Now given that, how do we calculate conditional expected payoff? Okay, and here I'm going to drop the negative sign. I'll remove it. So whatever calculation is basically utility, not disutility. Disutility, not utility. Right. So the actual payoff will be negative of whatever expression we are deriving. So the objective of each player is to minimize this rather than maximize its disutility. Within this interval, the action choice is x by 2, and the distance from the receiver's ideal point, which is theta, the state of the world, and the action is this difference, theta minus x by 2. And the disutility is the square of that. Okay? So that's the expectation that we have to calculate. Now, the density function is 1, the density within this interval is 1 over x. Remember that for a uniform distribution, the density is always the reciprocal of the length of the interval over which we have the distribution. So this is the conditional density function. So this integration gives us the expected value of this disutility. And when you calculate it, you get 1 over 12th times x squared. Of course, the disutility increases with the size of the interval and not linearly in a convex fashion, because if the interval is very broad, that means there's a lot of uncertainty, right? There's a lot of possibilities, but the receiver has to choose one action to fit all possibilities, all possible values of the state of the world, and as a result, on average, she's far off from her ideal point. If the interval was smaller, then no matter what theta is, the distance between the ideal action and the actual action wouldn't be that large. Okay, so this is the conditional expected payoff of the receiver, conditional on theta being drawn from a particular interval of length x. Right? Now, the second step, we have to put it together. We know that in equilibrium there are n intervals, right? And the kth interval is of length k. So if theta happens to fall in the kth interval, the expected payoff or expected disutility of the receiver is going to be 1/12 of yk squared. Yk is the length of the kth interval, right? This is exactly what we derived in the previous slide. So in the overall game, taking into account all possible values of theta, her expected payoff is going to be some weighted average of these conditional payoffs, right? Now, what is the probability that the kth interval is where theta will be drawn from? Well, that's given the nature of uniform distribution, that's just given by the length of the kth interval, right? That is synonymous with the probability that theta will come from here. So, if it falls in the kth interval, then it's 1/12 yk squared, that's the disutility, and the probability that it will come from the kth interval is yk. So we take the probability weighted average of these expressions. Now, that's a finite series, so you add it up, and you can again check it. I'm not going to go through every step of the calculation. Yk we derived previously when we were studying equilibrium, so there was an expression that we derived by solving the difference equation, if you remember. So we'll substitute that expression over here, and then we'll do the sum. And if we do the sum, it works out to be this expression. Okay, so we have derived an expression for the ex ante expected payoff of the receiver, right? Now there's this other player, the speaker, the sender, the expert who's advising the prime minister in our running example. So let's calculate the sender's welfare, and again the expected disutility in the beginning of the game, right? Even before theta becomes known at that point. So we'll do the same exercise. Consider any interval of length x. Suppose theta has fallen in that interval. We have uniform distribution throughout. For the sender, the disutility has this extra b term, obviously, because that's sitting in the preferences of the sender. So in our calculation, we have to throw that in. But the rest is very much similar or the same, except for this extra b term in the payoff function. And you do the integration. Again, I'll skip a couple of steps. You can check it out or fill up the detail. Once you do the calculation, you find that the disutility is this. So it is essentially the same as the receivers, except there's this plus b squared term, this extra term, which has been added to it. And now if you, again, follow the same sort of steps, now we'll take, the probability weighted average over all the intervals. And when we do that, we have to handle this extra term. The first term becomes exactly like that of the receiver. So the sender's expected disutility has two parts. One is simply the expected disutility of the receiver, and then a b squared term added to that. The b squared term is coming from the fact that on average, there's a bigger distance between the ideal action of the sender and the action which is actually chosen by the decision maker. So that it accounts for that. Okay, now so let's first focus on the receiver's welfare. Well, before I get to that, let me point out something. There's a lot of conflict between the sender and the receiver, captured by that parameter b, right? They don't see eye to eye. They don't agree. Even if they both knew what the state of the world is, they would not agree on what the ideal action is. And so in that zone, as I showed you earlier in a picture, in that zone between the ideal action of the receiver and the ideal action of the sender, they're pulling in opposite directions. Their preferences are not aligned. However, when we take into account how the game will be played out and look at ex ante welfare, right, in the beginning of the game, there's a perfect alignment between the interests of the sender and the receiver, right? So the sender's receive. So from this last line, you can see that if anything changes in the game which will increase the or decrease the disutility of the receiver, it will also pull down the disutility of the sender. So their ex ante interests are strongly aligned. And that is a very important feature that we'll talk about more. Now, let's go back to the expression that we derived for the receiver's ex ante expected payoff. You can see that it is increasing in n in the relevant range. So, well, first of all, if we fix n, right, and we slightly change b, what happens in this expression? Suppose we increase b slightly, and the same number of intervals is still possible. So we have fixed n. If we increase b, you can see that this expression goes up in value, so that means disutility increases. Yes. So this is something which I mentioned earlier, and it's intuitively clear enough. When the bias increases, even with the same number of intervals, the intervals become more uneven. They're more skewed. And that essentially captures less information. So The receiver learns less useful information in equilibrium, and that is one source of welfare loss from increasing bias. Another point to note is that the most informative equilibrium generates the highest welfare. Now that is not immediately obvious if you look at the expression, because n is in the numerator of the first expression and in the denominator of the in the numerator of the second expression and in the denominator of the first expression. So the two things are changing in opposite directions. But if you take the derivative of this with respect to n, suppose you differentiate, you will find that the derivative is decreasing up to a point. In particular, remember that the maximum number of intervals is some nb, and in an earlier slide you have an expression for that. Right? In equilibrium, you cannot create more than a certain number of intervals. And what you can show is that by differentiating, that this expression is decreasing in n up to that point. Okay? So in the relevant range, disutility goes down as n increases. So what that means is that you have these multiple equilibria, right? You have an equilibrium with n equal to 2 and 3 and 4. The equilibrium with the maximum number of intervals possible is the one which generates the highest ex ante welfare and the lowest disutility, right? So if you believe that they will play the best equilibrium in terms of welfare, then that's one reason to look at the equilibrium with the maximum number of intervals. Okay. Now, the last 2 points are extremely important. So let's think of 2 kinds of commitments. All right. So for example, the sender, just to sort of indulge in a thought experiment, suppose the sender, before the game started, could publicly inject himself with truth serum, right? Some chemical which makes us tell the truth. We cannot help but tell the truth. We become honest due to the effects of the chemical. So suppose the sender could do that, right? So sender hasn't yet learned theta. The sender knows how the cheap talk equilibrium works. And at this point, the sender can, in front of the receiver, take the truth serum. Will the sender want to do that? And to answer that question, of course, we have to apply the criterion of ex ante or expected welfare, right? So expressions that we have just derived. So let's go to the receiver's thing. Okay, so what happens if the sender takes the truth serum? Then the receiver believes everything the sender says, right? Because the receiver now knows that the sender cannot help but be honest. So she'll report the true value of theta without trying to manipulate things. So whatever theta is, that is what the receiver will choose. And so the distance between what the sender wants, which is theta plus b, and what gets chosen, which is theta, is always going to be b. No matter what theta is, there will be this gap of b between the sender's ideal action and what the receiver will choose. So, what is going to be the ex ante welfare of the sender? It's just going to be b squared, right? So, if she doesn't take the truth serum and plays out the cheap talk game, then the sender's payoff is going to be this expression. In fact, I should go to the next slide. And so if she doesn't take the truth serum and plays the cheap talk game, her payoff is going to be b squared plus this term, right? So it's going to be more than b squared. And if she takes the truth serum, then her disutility is simply b squared. So taking this truth serum, therefore, is helpful. It makes the sender better off ex ante. So that establishes this principle in this sort of model that honesty is the best policy. If you could somehow commit to honesty, it'll make you better off as the speaker. However, it requires commitment. Because after learning theta, there's a temptation for the sender to change around matters, right? Now, the truth serum is, of course, a silly example to just illustrate these things. In reality, players often commit to revealing all information. For example, governments can commit to full honesty or transparency by passing something like the RTI Act, right? Right to information, that they will not hold back any information. They will reveal all the document and in a verifiable way, right? So that's commitment to honesty. So here we see a sort of strategic rationale for something like the Right to Information Act. Of course, we as citizens will benefit from it, but if the government has a somewhat different objective from us, this is saying that even the government itself will benefit from committing to honesty through something like an RTI Act. So that's one point. The other point is that we could think of similar commitment possibilities on the side of the receiver. So what if, now let's switch around roles, the receiver before the game starts could hand over the keys to the sender. The receiver could delegate decision making to the sender. The receiver could say that, well, you know what the state of the world is, so I'm handing over authority to choose the action to you. And I'm not going to meddle, I'm not going to come back and take away the keys from you. You decide what action ought to be done, right? So in the cheap talk game, the sender has an advisory role, not a decisive role. The sender can only advise the receiver through messages. But if the receiver delegates decision making, that means the sender now has the power to choose. So what happens to the receiver's ex ante payoff if he delegates the decision making? Now there, if delegation is done, then the receiver's payoff is going to be minus of b squared, right? Because for every state of the world theta, the sender will choose theta plus b. The receiver would have wanted theta to be chosen. So there's a gap of b. And so the disutility is b squared no matter what the value of theta is. And so it's b squared in expected terms. Now, if the receiver doesn't delegate and decides to go ahead and play this game, then in this game, this is the expected payoff of the receiver. Now, suppose b is small enough so that we have more than a babbling equilibrium. We have at least a two-message equilibrium, right? Or more. So for example, if you have a two-message equilibrium, if n equal to 2, then this becomes 4 minus 1, 3. So the second term here becomes just b squared, and added to that is how much is it? Added to it is 1 over 48. Okay? So the receiver's expected payoff from the game is more than b squared, at least as long as the game has non-babbling equilibria. And let's at this point focus on those cases. So if there's a non-babbling equilibrium, then by playing the game, the receiver has a disutility higher than b squared. And if she hands over the keys and commits and delegates, then her disutility is just b squared. So of course, it's better to hand over the keys. So that comes, that's the explanation for this last bullet point, that from the sender's side, honesty is the best policy ex ante, but not ex post, right? If you could inject the truth serum, if you could write down an RTI act, then he would want to do so. But it requires commitment, because if you haven't committed, if you haven't passed the RTI law, then once you know the information, he will want to manipulate, and we'll be back to square one. We'll be back to playing the partition equilibrium. And similarly from the receiver side. So from the receiver side, power is valuable ex post, but not ex ante. Right? Once the receiver, if the receiver has delegated and he sees that the sender is about to choose a certain action, let's say 0.4, right? And suppose our B is 0.1. Then the moment the receiver sees that the sender is about to choose 0.4 as the action, the receiver immediately knows that the true value of the state of the world is 0.3. And at that point, the receiver will have a tremendous temptation to snatch the keys away and change the action from 0.4 to 0.3. Yes? So what commitment does is that it ties the hand of the receiver and prevents the receiver from making this alteration. Because if the receiver could make this alteration, then the sender will, start the usual nonsense of speaking in broad categories, and we're back to square one once again. So what's happening in this model is that there are two important elements. There's power, who can take the decision, and then there's information, right? Information determines what the optimal decision should be. Information along with preferences. And we have taken a very stark model where power and information reside in different players. One player has the power to take the decision, but doesn't have much information. And the other player is very well informed, but doesn't have the power to take the decision. So what we are seeing here is that an institutional arrangement which marries power and information, right, confers them in the same player. The same player becomes informed as well as powerful. Any kind of institutional arrangement which creates this sort of convergence is going to be best for everyone. It's going to be welfare improving. It's going to be a Pareto improvement. Both parties will be better off. Yes. So whoever holds the key to information, namely the sender, has an incentive to give it up through a commitment, and whoever has the power, namely the receiver, also has a similar incentive to give up the power to the informed party. And that's a very important lesson, that institutional arrangements where power and information remain separated are often inefficient in a very strong sense, in a Pareto sense. And so bringing them together by reorganizing things is going to be good for everyone.